Hi everyone. As we prepare to get started, I'd like to encourage you to open these slides on your own browser so you'll have them available to refer to later. There are also a number of links you may wish to click on. So the URL you will want is shown there on your screen. And I know it's hard to tell, but there are underscores between the words in this URL. And this first slide is just to help you navigate this slide deck if you look at these slides on your own. And there are ample speaker notes. So if you missed something that I said, there's a good chance that anything that you missed is going to be in the speaker notes of that slide. Thanks again for joining us and welcome to our session today. I'd like to begin by briefly introducing myself and introducing Arcus for those of you who may not be familiar with us. My name is Joy and I use she, her pronouns, and I'll be leading today's session. I've already talked a little bit about Arcus in the first session of this skills series, so I'll just skip most of that this time and simply say that Arcus is an initiative by the Research Institute aimed at promoting data discovery and reuse and increasing research reproducibility. You can find out more by checking out the Arcus application itself or the Arcus SharePoint site, which has a calendar of events and lots more information about Arcus. And finally, a little more about me. I work in Arcus education. Our role is to support CHOP scientists by helping researchers acquire data science skills. And that's why we have skills series like this one. The Arcus education team does lots of different kinds of education. We work one-on-one with researchers in office hours. We write how-to guides to help people understand how to use Arcus tools. We create asynchronous modules that people can use to acquire skills in their own time. And we do synchronous events like this one. Please check out that education page and find out more about some of our services. You can see that I've added a screenshot of that page to the slide here on the left side. You can also email us at arcus-education@chop.edu. One of our methods in education is the skills series, and that's what you're in today. In this series, we're going to take just 2 sessions to help demystify R and RStudio. If you've heard people talk about these concepts and you have only a vague idea of what they are and you want to learn more without having to actually download anything or write code, at least not yet, this is the right series for you. After you finish these 2 sessions, you'll understand what R is, what RStudio is, why people use these tools, and next steps for getting access to them and using them if you want. So let's get started with this second session. In this session, we're going to cover the concept of literate statistical programming and why it's a great practice for data analysis. Literate statistical programming can be done in various languages, but we'll talk about how to do it in R using RStudio in this webinar. My goals today include your being able to describe what makes programming considered literate. I hope you'll be able to explain the real-life consequences of irreproducible research. And I want you to be able to name one way that Quarto documents can be helpful in data analysis. Now, let's start with a quick review of some of what we talked about in the first session of this 2-part series. Last time, we made an important distinction between R and RStudio. The first logo you see here is for R. R is a statistical programming language that's great for doing data analysis. We talked in the first session about a few things that make R useful. It was built specifically for statistical data analysis, so it's got a friendly and focused user community and lots of great online resources for learning. R is open source, which means that it's free in 2 ways, in the meaning of having no cost, and also in that it can be used freely, without intellectual property concerns or licensing restrictions. R makes it possible to work with data and build scripts that do lots of things, from ingesting data to building data visualizations, and lots of steps in between. So that's R. It's a language with a lot of benefits. Then there's RStudio. RStudio was the original name of a company, as well as the name of a piece of software the company makes. A couple of years ago, the company changed its name from RStudio to Posit, but they kept the old name on at least some of their software. You can think of RStudio, the software, as a fancy text editor for writing R code. The technical term for a fancy text editor for writing code is Integrated Development Environment, or IDE. You don't have to use RStudio to write R, but it makes it a lot easier. Last time we gave the example of typing a paper in Microsoft Word. If you didn't have Microsoft Word, you could write your thoughts down in the Notes app on your phone. But Microsoft Word has lots of add-ons like spell check and word count and formatting that make it much more pleasant to write a manuscript there rather than in the Notes app on your phone. One of the things that you can do in RStudio really well is write code in a particular paradigm called Literate Statistical Programming. And that's what we're going to talk about next. Literate statistical programming is a great way to make sure that your data analysis steps can be done in the future with ease. Let's explain this term a little bit. Literate programming was coined decades ago by an important figure in computer science, Donald Knuth. He realized that while computer code was obviously being consumed by computers, it was also being consumed by humans, and it needed to be readable. And code needed to be better than barely readable, but instead actually be fluid and easy for humans to read. Literate programming relies not just on a short, cryptic comment here or there, but on real documentation that is interlaced with code. When we combine that concept with the idea of statistical programming, where we're analyzing data, we get literate statistical programming. Literate statistical programming is what you do when you create a script, say for instance in R. In that script, you go through the steps of writing code that handles ingesting data, cleaning and analyzing it, and displaying your data and findings. And you also think about how best to describe what you're doing in human language, with full paragraphs and headers and figure captions and bulleted lists, and maybe HTML links out to helpful documents, and other notes that help you remember and help others learn what you're doing and why. Let's show you an example. Last time we showed you some of our analysis code my team uses to analyze our effectiveness in a webinar we give called ARCUS 101. Here is a snippet of a script we wrote, and you can see that it has some description of what the code is doing to help humans. We put in a header to separate a section that has more to do with bringing the data in and cleaning it. Then we write a paragraph describing what we're going to do, followed by a chunk of code. After that code executes, we'll have some data. So we have some additional steps described, this time in the form of a bulleted list. I'm not showing you all the code that makes that bulleted list happen because it's kind of long, but the code chunk with the gray background below that bulleted list includes the code that does all the things in the bulleted list. Hopefully what this does is make it a lot easier for anyone on my team to pick up this code and work with it, even if they're not the person who wrote the code. This is what literate statistical programming looks like, and working in R and RStudio is a great way to get started working in this paradigm. This can help you create a kind of lab notebook that records each step you do with your data, in human language and in computer language. This is part of doing reproducible data analyses, which will reduce risk and make future you much happier. And I do want to talk briefly about the very real risks that can happen when people don't do reproducible data analyses. Consider the following case study, which highlights potential consequences of irreproducible research, or research that's really hard or impossible to redo in the same way. A few years ago, researchers at Duke University tried to use gene expression data of tumor cells to predict sensitivity to chemotherapeutic agents. This approach generated a lot of excitement at the time, and the resulting work was published in high-profile journals. Unfortunately, there were a number of serious errors in the data analysis. Even more unfortunately, patients were enrolled in clinical trials and allocated based on flawed models. It's likely that some patients were actually treated with the chemo they were least likely to respond to, rather than the chemo that was most likely to work. In the end, 18 papers were retracted, and Duke settled more than 10 lawsuits for an undisclosed amount of money. Two biostatisticians at MD Anderson uncovered these mistakes in painstaking effort. Let's look at one of the errors they found. What you see on the left are the names of a few of the hundreds of microarray probe sets. Each roughly corresponds to a gene that the Duke University investigators reported to predict sensitivity to a particular chemotherapeutic agent. And on the right are the probe sets that the MD Anderson team got. You can see that they're not the same. Can you see what went wrong? If you look closely at the values, you might notice a pattern. The number of the probe set that Duke reported is always one less than the number of the probe that the MD Anderson team found when they redid the analysis. This is what's called an off-by-one indexing error. This happens when you use a tool like Excel and accidentally miss one row, or you have one data set that has a header and another one that doesn't. The result is that all the values in the affected column are shifted by one. This is a simple error to make, but it completely invalidates all downstream results. A key issue in this case study is that the Duke investigators used point-and-click tools like Excel without automated scripts, without using a literate statistical programming approach. There was a lot of manual human intervention here, things like the use of spreadsheets, work that was really labor-intensive and had lots of steps, many of which were probably never written down, but just kept in people's heads. This prevented peers and independent investigators from catching errors in the analysis until it was too late. Unfortunately, the Duke case study is only one example where the barrier to reproducibility was that people used point-and-click type tools for analyzing large and complicated sets of data. There are lots of other examples where point-and-click analysis has resulted in analyses being wrong. Now, with the right safeguards, Excel can be the right fit for some simple tasks, but for high-stakes things like research results, it can hide your mistakes and compound them, and no one wants that. Using scripts to document your work in a literate statistical programming approach doesn't only help people outside a study understand how things were done. They can also help your local team, even if you're just a team of one. Consider the following three statements and ask yourself if they sound familiar. Can I redo the analysis with this month's data? And can I do it in a hurry? Why do the data in Table 1 not seem to agree with Figure 2? And why did I decide to omit these 6 samples from my analysis? Keep in mind, your closest collaborator is you from 6 months ago, but past you can't answer your emails. If you use literate data analysis scripts in R, scripts that record each step you do in code and in human language, it can be much easier to retrace your steps or rerun your entire analysis with just a couple of clicks to rerun the script. You could, for example, have a script that goes and gets the latest data directly from REDCap, removes any outliers according to pre-established rules, does some statistical tests on 2 groups, creates a table and a data visualization, and saves all of that in a PDF that is already formatted with the special rules of the journal you want to submit to. You could keep collecting data via REDCap and simply rerun that script with a single click and get an updated report. This will make your life easier in the long run, even though it means an upfront investment of writing code. I hope I've convinced you that literate statistical programming can help make your data analysis more reproducible, and that this can have really important consequences. One way to start doing literate statistical programming is to use Quarto. And another is a very similar document format that preceded Quarto and is very much like it, called R Markdown. My team's code that analyzes our survey data, the code you've seen already, is a Quarto document. Quarto and R Markdown allow you to write computer code mixed in with human language that documents the purpose of the code and details about the decision you made in your analysis. Quarto documents are composed of 3 basic types of building blocks. The first is the header, which includes information about the document, such as its title, author, and the desired output format when the document is rendered. A lot of this information is optional, so a header can be pretty short, like the one we see here, or much longer. The second type of building block is text. Text can include special kinds of marks called markdown that add styling. This includes hash marks that turn a line of text into a header, asterisks that can create italics, lines of dashes that turn into horizontal lines, and much more. Markdown is used everywhere in tech, not just in R Markdown or Quarto. Markdown is useful to learn if you're going to use GitHub or Python or LaTeX or make posts on Stack Overflow or use Reddit or just about anything in the tech world where you're expected to write some sort of documentation. The third unit is code chunks. Code chunks contain R code that can be executed to output results. You can use a Quarto or R Markdown document interactively and run code from within it. You could run a single code chunk to ingest data and just stop there, for example. But you can also use this kind of script to make a final output document, like a short HTML file, a slide deck, a manuscript you want to have in PDF format, or even a whole website. In fact, the online slide deck I'm presenting from right now was built in Quarto. These slides, which use HTML and JavaScript, were written in RStudio using Markdown. And if I wanted to, I could run R code inside these slides. To make an output document, you click a button in RStudio. The button might say Render or Preview or Knit, depending on the kind of document you're creating, and whether you're working in Quarto or R Markdown. The words all kind of mean the same thing. If what you've learned today, and possibly in the first session of this series, has inspired you to want to learn to write R code and to use RStudio to do that, there are lots of ways to move forward. First, do get access to R and RStudio so you can begin to use those tools. Posit.cloud is an online service that has a generous free tier and will allow you to practice your R and RStudio skills without downloading anything. But you should never use this for real work data. Or you can get software installed on your CHOP device. We'll share some slides about how to do that in just a few moments. Second, learn how to use R. We strongly suggest starting by learning about working in tabular data using the tidyverse. Even if your eventual goal is to do genomics or computer vision or machine learning in R, starting with tabular data analysis using the tidyverse set of packages will help establish good habits and give you a good foundation. Also, we want to reassert that while RStudio is optional, it is highly, highly recommended. You should learn within the context of using RStudio software because it has a lot of helpful scaffolding that will make your experience less frustrating. Now, where should you go to learn R skills? My team has some offerings here at CHOP, but we're certainly not the only game in town. How do you like to learn? Are you motivated by grades and you really thrive in a class setting? Many universities offer courses in R, often related to things like biostatistics or public health. Do you like videos and short-form courses that you get a certificate for? Coursera and other massive open online course providers have great R courses, which again can sometimes be related to a specific interest, like Bayesian statistics or data visualization. Do you prefer books? There are some great books out there, especially ones by people like Hadley Wickham and Garrett Grohlmund. In the next few slides, we'll have some other links for CHOP-based resources, but please know that there's a wealth of other stuff out there that you may also really enjoy. CHOP also has had an R user group for a number of years, and we encourage you to join it. There's a mailing list as well as a Slack workspace that people use to communicate, share successes, ask questions, and get advice. Learning to code is like learning a sport. You have to do it repetitively and build muscle memory. So take something you do regularly, whether that's analyzing your department's budget, or reporting on recruitment for your study, or looking at infection prevalence on your floor, or even looking at the data from your favorite sports team or political party. Take one thing that you do using a point-and-click manual approach and try to move it to analysis with R. At first, you'll feel like it's awkward and hard, like you're writing with your non-dominant hand. But after a while, you'll gain skills and figure out how to apply what you've learned to other tasks. And finally, writing code is difficult, but your whole job is hard, or at least it was hard at first before you developed the skills, right? So when it feels like you keep making mistakes, I want to encourage you by saying that I fail too. I not only write R to analyze data, but I teach this stuff, and I still mess up. I have to Google things, I have to ask for help, and I constantly learn new things from my colleagues. So please be kind to yourselves as you continue to learn. There are some detailed slides that we went over in the first session of this series, and I'm just going to give those links here. Please check these out because these slides have helpful next steps for you. The first 2 slides are general purpose and describe how to get R, RStudio, Git, and GitHub installed. The third slide is of particular use if you work in research, and the fourth talks about posit.cloud. And as promised, a few links here. You can join the R user group using this link. You may also want to check out some asynchronous modules my team built, which you can use to learn R in small bits of time, like on your lunch break. Additionally, we plan to have additional skills series like this one. This skills series was a short one of only 2 sessions, but our next one will be entitled First Steps in R and RStudio, and will be 5 sessions in length, and will help you get started writing code for the first time. Keep your eyes open for announcements about that in the R user group or on the Arcus SharePoint page. Now, this is not the final slide, but we're a group that likes to measure our effectiveness and make changes based on what we learn. So before we do questions and answers, we like to make sure to give our learners a poll to see if we made a good use of our time. So if you're in a live session, we're going to ask if we were effective in reaching our goals today and give you a poll on your screen, asking how well we were able to meet our goals for this session. So as we get close to the end of our session today, I know that for some people, this topic ignited a bit of excitement around the ideas around learning how to code or learning more about reproducibility. So I've added a couple of asynchronous modules here on your screen, as well as R basics. And these are all examples of some of our asynchronous modules, which I mentioned earlier. And there's over 60 of these. So try checking them out to see if you like this style of learning. And if you're an Excel user and you want to understand the risks of using Excel and how to mitigate them, there's an article here that might be interesting for you to read. Finally, we want to thank the people that contributed to this work. The CHOP R user group leaders, especially Stefan Kodaki, created some of the materials that we started with years ago that have changed over time and have morphed to include some of the materials that we presented today. We're grateful to all the students at CHOP and beyond who have taken our workshops with my team and given us valuable feedback that has improved our approach. We especially want to highlight our DART study participants and thank the NIH for funding our research efforts in how to upskill biomedical researchers in data science skills. We really enjoy the humor and science of Ed Himmelblau and are grateful for his generosity in supporting our work with his art, which was featured in our first session of this series. And of course, we want to thank you, our participants, today. With that, I want to thank you for your time and enthusiasm. Your time is an incredibly valuable and non-renewable resource, and I hope that this webinar series was a good use of your time. If you have any feedback, positive or negative, that you'd be willing to offer, that would be a great gift for my team and for me. So please feel free to drop my team a line, and you can do that by emailing arcus-education at chop.edu. Thanks so much.